Okay, next we discuss about the heat equation. The heat equation is dou u by dou t is equal to c square into dou square u by dou x square. If you compare it with the wave equation was dou square u by dou t square is equal to c square into dou square u by dou x square. That means both sides had the second order derivatives, whereas in heat equation the derivative with respect to time is of first order and derivative with respect to position is of second order. And in wave equation this u was the displacement of the rod, whereas in heat equation it is the temperature of the rod. Of course in wave equation it was a string. Okay, in heat equation the background is this, that is we have a rod, a uniform rod with a lot of assumptions. So uniform rod means it is made of the same material, and the area of cross section at each point is going to be the same. So and if you take such an area of cross section, all the points in that cross section will have the same temperature. That's also one of the assumptions. And we'll assume that the rod is laterally insulated. That means the heat cannot escape through the sides, but it can escape or enter through the end points. Okay, so we usually provide sources means the heat sources at the end points. Okay, lateral sides you cannot, and also heat cannot escape through the lateral sides. So in such a case, suppose you place some sources on both sides, then what will be the temperature of a point? Point means that point is of a point of the area of cross section, right? So at each point of the area of cross section we assume that the temperature is the same. So the temperature at a point, say we call that temperature as u, and it is a function of the distance of the point from one end. That means if you heat the rod at this end using some 60-degree temperature and this end at 80-degree temperature, then the temperature at these points will be different from the temperature at the right side, right? Because here you have 80-degree and here you have 60-degree. So temperature definitely depends on the position of the point at which we are looking at, and also it depends at what time we are observing, at what time after the initiation of the process we are observing this procedure or observing the phenomena. So that time and position, these are two variables. As in the case of wave equation, the same variables are here, position as well as time. So the wave equation says that dou u by dou t is equal to c square into dou square u by dou x square. This is the equation ruling the temperature distribution of this rod. Okay, so how do we solve this is the question. So u is representing the temperature at a cross section, and the rod is a thin bar with uniform area of cross section, etc. And the temperature at the ends need not be zero. For example, in the wave equation the initial point and final points were tied at some fixed wall or something, so they will not move, right? So the displacement at endpoints were zero, but here it is not mandatory. In some cases we will assume that both the sides are kept at 0-degree temperature. That means you keep an ice cube on the left side and right side, then observe the temperature. Then what happens is the temperature will decrease, because otherwise they will be, all the points will be in the room temperature, but whenever you keep an ice cube on the left side and right side, the temperature of each point will start decreasing, right? So that depends on the conditions, initial conditions. Unlike wave equation, we will not have a specific condition at endpoints here, unless the problem is fixed. That means for a problem the initial conditions are to be mentioned specifically. So we'll solve the heat equation without having any initial conditions, without assuming any initial conditions. Okay, so for solving the heat equation we adopt the method of separation of variables. That means we assume that uxt, which is the temperature distribution, can be splitted into, or it is a product of x of x and y of instead of y of t I am using t of t. Okay, so then as I said, the heat equation is dou u by dou t is equal to c square into dou square u by dou x square. So dou u by dou t, if you see from here, dou u by dou t is actually x into t dot. T dot means the derivative dt, d capital T by d small t. So that comes in the left side, because the wave equation is this. So here it will be x into t dot, and the right side will have x double dash into t if you follow the method of separation of variables. Okay. Now what you have to do is you have to separate into both sides. So x double dash by x is equal to t dot by c square t, and since the left side and right side are now in two independent variables, both of them must be equal to the same constant k. So it should be equal to k. Now you have the situation where k is positive, negative or 0. Okay. So we will see these cases one by one. So first I assume that k is equal to 0. In that case I am going to solve these two equations independently, that is x double dash by x equal to k and t dot by c square t equal to k. So what happens if you assume x double dash by x equal to k? K is 0, right? In this case k is equal to 0. Therefore what happens is x double dash is equal to 0. That if you integrate twice, you will get x of x is equal to c1x plus c2. First if you integrate, you will get x dash x equal to c1, a constant. Once again if you integrate, you will get this. The second equation is t dash by c square t is equal to k is 0. So t dash is equal to 0, because if you multiply the c square t to the right side, you will get t dash equal to 0. So that means t must be equal to a constant. So the solution in this case is uxt is equal to x of x is c1x plus c2 and t of t is c3. Now if you club the c1 into c3 and call it as a, and the c2 into c3 you call it as b, then the solution is now uxt is equal to ax plus b. And this case is called equilibrium case or a steady state. Actually it is called a steady state. Why it is called a steady state is the temperature is not changing depending on time. The temperature is just a function of x, right? In t there is no t here. So as time elapses, the temperature is not changing, but of course it will change depending on x. So that is why it is called a steady state. Steady state is a state in which things are not changing with respect to time. So that solves the heat equation when k is equal to 0. Now we see the other case, k is positive and k is negative. Other two cases. So case 2, k is greater than 0. So in that case, as in the wave equation, you can take k equal to alpha square, where alpha can be assumed as greater than 0. So again the first equation gives you x double dash is equal to alpha square x, or x double dash minus alpha square x equal to 0. So the auxiliary, say second order ordinary differential equation, because you have capital X as the dependent variable and only one independent variable, which is small x. So it's an ordinary differential equation, second order ordinary differential equation with constant coefficients. So auxiliary equation is m square minus alpha square equal to 0, and m's value are going to be plus alpha and minus alpha. And since they are real distinct roots, the solution of x, capital X in terms of small x, is going to be c1 e raised to alpha x plus c2 e raised to minus alpha x. Now you go for the second part of the equation. So t dash by c square t is equal to alpha square. So that gives you t dash is equal to alpha square c square t, and this left side you can take as d capital T divided by d small t is equal to this. So you do variable separable form, and then you can see that t dash, after making it variable separable, that is d capital T by d capital T by capital T is equal to alpha square c square d small t. Then integrate it, you will get t of t is equal to some constant c3 into e raised to alpha square c square t. Therefore the solution is going to be uxt is equal to c1 e raised to alpha x into c1 e raised to alpha x plus c2 e raised to minus alpha x is the solution for x of x. So you multiply x of x with the t of t. So t of t is c3 into e raised to alpha square c square t. So c3 e raised to alpha square c square t. So c1 into c3 can be assumed as another constant, capital A. It's an unknown constant. C2 and C3 are unknown, so they can be clubbed together and form B, the new constant B. So this is the solution in this case. Okay. So this solution is actually not that meaningful, because the temperature at a point cannot increase rapidly. This is actually exponential increase, right? So everything is in exponential terms. So exponential increase in temperature is actually not practical. That's why this case is actually useless. Now the third case, wherein k is less than 0, say k is equal to minus alpha square for alpha greater than 0. So there again you can form the auxiliary equation, or the equation in x will become x double dash plus alpha square x equal to 0. So m square plus alpha square equal to 0 is the auxiliary equation. Solving it, you will get complex roots 0 plus I alpha and 0 minus I alpha. Therefore the solution is capital X of x is equal to e raised to 0x c1 cos alpha x plus c2 sin alpha x. Now second part, that is t dash by c square t is equal to minus alpha square. Again you can make variable separable. Then the solution is going to be t of t is equal to c3, some constant c3 into e raised to minus alpha square c square t. And therefore the solution is going to be the product of these two. And here also you can club this c1 and c3 and write it as a, and c2 and c3 can be clubbed as b. So the solution is uxt is equal to a cos alpha x plus b sin alpha x into e raised to minus alpha square c square t. And from here, if you want to proceed, you must know what are the boundary conditions. Now, if you have the boundary conditions like both ends are kept at 0 degree, then you have u0 t is equal to 0 and ult equal to 0, and proceed as in the case of wave equation. Without knowing the boundary conditions, you cannot proceed the problem. Okay. And there are cases in which first we will provide some temperature on both sides, non-zero temperatures on both sides, and wait for a case when it reaches the steady state, and then we will start observing the temperature distribution by removing the sources. These are all coming in problems. So theoretically we can solve up to here. That is, we have to start from this solution when you go for problems. Okay, this solution, or if it is going to steady state, you have to take the case when k is equal to 0. That depends. Okay, so that's all about wave equation. We will see some problems also. Thank you.